Hi everyone, today we will discuss our teamwork of Australia election data analysis. Our team was divided into three parts. One part is responsible for the front end and the second part is responsible for the back end. And the last part is responsible for data collection. We would display 5 parts as follows. So let's talk about the first background and overview of the subject. So we choose this topic from 3 dimensions. The first dimension is national significance and level of interest. We can see that we have 2 key points. The first one is the Australia federal election is of great national significance. And the second one is high attention from all levels of society. And the second dimension is rich database. We collect abundant data from social media, such as Mastodon and Blue Sky, and also collect data from mainstream news media and official channels. And the last one, we can collect data also from large amount of data and diverse sources. And the last dimension is multi-dimensional analysis potential. We can also see 3 key points for sentiment analysis and topic mentoring and public opinion tracking. So we would display what part is each of us responsible for. From the picture, we can also see 3 main parts. I do the data integration and front-end technology with Steven Chen and Yihao Sang. Yuan Gao and Yao Zhao are main responsible for the back-end processing. The core of this section, we can see the core of this section is to capture external social media traffic, such as this. And the last, we also use Jupyter Notebook to display the graph and the picture. Everyone in our team has their own role and responsibilities.
Okay, let's turn to the second part. In this part, I will introduce the front-end component of our election sentiment analysis system. Our front-end was developed in Jupyter Notebook and includes 4 main functional modules. First, the map visualization module displays the geographic distribution of posts and their emotional intensity across different Australian states and cities. It supports both corpus and heat map layers. Second, the sentiment statistics module shows how emotional responses differ across states using bar charts. These charts update dynamically based on the select time range. Third, we have the word cloud analysis module, which extracts the most frequent keywords from social media posts. We also use the custom mask shaped like Australia for better visual design. Finally, the date range selection module allows users to define custom time ranges or use one-click options like before election and after election, or just respond in real time. Yep. So why does this matter for users? First, it helps users understand sentiment trends at a glance without reading any road tests. They can also compare emotional changes before and after the election and identify regional differences in sentiment. The word cloud helps them quickly focus on hot topics, which is useful for journalists and researchers. And most importantly, the interface is very easy to use. It's very simple, with simple buttons and sliders. Okay, now we turn to technology part. We use Jupyter Notebook as main interface with IPI widgets, plotting interactive controls. The map is built using volume and GeoJSON, and the bar charts are created with Seaborn and Matplotlib. The word cloud is generated with NLTK and word cloud combined with stop word filing and line extraction. All data is queried from Elasticsearch based on the user's select time range This stack allows us to build responsive, interpretable, and user-friendly front end without any complex frameworks. And now I show the demo how to use Jupyter Notebook to show our front end. Okay, now you can see the map and the sentiment chart and the word clouds. And you can choose the start time, start date. Is the example for March 5 to March 16. Yeah, now you can see the date range changed from 3 graph. Okay, that concludes the front-end presentation. Thank you.
To analyze change in public sentiment before and after the Australian election, we searched many different social media platforms. Finally, decided to choose two famous and large platforms, Mastodon and Blue Sky. In Mastodon, we collected data for 6 months before and after the Australian election, and get and update consistently data from Blue Sky after election. For keyword selection, not only choose some hot keywords like Australia election, AUS poll to get largest part of data, but also we choose politics word like candidate name and party name to ensure data integrity, such as Dalton and Labour. After keyword selection, we browsed to two platforms to find data flats we need. Mastodon raw data flats include ID, created time, location, and so on. For Blue Sky, we get author, time, likes, this is data, and so on. And then we confirm data fields. We program Python scripts using API to get data at regular intervals. According to raw data, we further clean and process the data. We firstly normalize the field, change time format to UTC time zone, and generate post time of day, include morning, afternoon, evening, and night, according to created time. The most important thing in the process is that clean content using clean HTML content function to remove HTML, keep plain text only. Besides, we handle missing value like geologic through data augmentation to fill the information. In terms of invalid data elimination, we remove poses with empty content and word less than 10 characters. At the same time, we filter some posts created by robots automatically to pure data. Finally, we use test-bot function to analyze sentiment scores and use emotion functions to classify as positive, neutral, negative, this is label. The parameter table is data we use eventually.
Hi, this is Gavin. I'm going to introduce the system architecture part. And the whole architecture is divided into 3 parts. The one is outside and the 2 are inside. The first part is Nectar and cluster, which is the infrastructure of the whole process. We deploy Kubernetes cluster on the Nectar so that we can easily access and control the cluster and carry out subsequent development. It's very important. And then the second part is the Elasticsearch cluster deployed in the cluster Elasticsearch namespace and the Fission service in the Fission namespace and notebook service in the notebook space to support the front end. And for the Elasticsearch parts, this service has a primary node and a replica to do the backup nodes and to ensure the fault tolerance and high availability, which is very important in cluster deployment. And with the user-facing client locally to send commands and execute functions in the cluster. The third part is external website web service like Mastodon server. We use API to interact with it and get some JSON data, and we use GitLab to load our Web3 in the notebook. Then I'm going to introduce the Elasticsearch data stream. And as you can see, the first this data flow is divided into two parts as well. The first part of data flow from the external server, and the fishing functions request and extract the raw data from the external server in an in-stream data processing pipeline using the external data source API like Sport Sky. It do the data harvest and then do data incremental by a temp trigger. After we harvested the raw data, the site commander will start it. This raw data will be taken out by the other set of fishing functions for further processing, including format transformation, data cleaning, granularity, aggregation, etc. And then all the data will be continually written into the final index in Elasticsearch, as I show in the table, election V2. And finally, I'm going to introduce the fishing functions. These fishing functions is mainly divided into two parts as well. And in the two parts, data flow of Elasticsearch. So data source can be external data and or the internal data source. The fishing function can fetch historical data or the incremental updates, and the target database in the location of the target database. And when we pull the historical records, the other is the other is updating the real-time data. And the updating is triggered by the fishing function by the citing the temp trigger timed to compile the temp steps, putting the latest updated data within the API and updating the latest raw data to the final business. The whole process uses a synchronized mechanism which improves internal coupling and reduces external coupling. This design improves the separation between different functions, makes the whole data flow in structure clear, and also makes subsequent business expand easier, as we only need to expand a certain data flow, not modify the overall data flow. It's very crucial design in our project.
Here I'm going to introduce you some of the backend development. At the start of the project, we identified the requirements for our backend content. In the first place, we should build an updated database. And secondly, it should cover multiple information resources. And moreover, it's obtain a real-time feature and data trace feature. Accomplishing all those three goals relies on the two main mechanical details. The first thing is the fishing function and time trigger schedule task. And the second thing is distributed crawling for the different sources, independent incremental logic. Let's take our Blue Sky data crawling process, for example. For Blue Sky data, we took a hybrid approach of two crawling strategies. The first strategy is by using a cursor mechanism. We can recurse the cursor returned by the API at the end of each data fetch and continue retrieving new data from that cursor in subsequent requests. Specifically, we receive a state doc ID in an Elasticsearch document which not only stores the current cursor, but also tracks the batch number and the total number of processed items. Each task is executed in one or more batches. In each batch, data is fetched from the API using cursor-based pagination until either the set batch size is reached or the API no longer returns a new cursor. For each new batch, the last saved cursor is used as a parameter, and the API returns an updated cursor, making the process progressive. After each batch, the new cursor is saved, allowing the next round to resume exactly where the previous one left off, ensuring that no new data is missed. The second approach uses the earliest time step threshold as a history paging. At each time, we only fetch data with time steps earlier than the previous minimum, gradually moving back through history to ensure there is no overlap. An ES document is used to save a state doc ID, which records only the earliest time step captured in the last round. For each graph, the process reads the saved it and only handles posts older than these time steps. During the crawl, the minimum time step encountered in the current round is updated in real time. After the crawl complete, this new earliest time step is written back to ES to serve as the starting point for the next round. It's clear that the first method is more suitable for real-time or continuous capture for new data, and the second method is more suitable for historical data archiving. And after the combination of the two approaches, these all achieve the complete mining of Blue Sky data. After obtaining the initial data from Blue Sky and Mastodon, we established a dedicated index for business analysis and front-end display. We used the Fission's time trigger feature to set the incremental data part to run regularly, and at the same time, we set up a function to regularly read the two incremental database into newly created index. All those above achieves continuous database updates.
先结束啊，
没错没错，
先结束共享。
我们来看一下。看看更多情况。